Okay, so yesterday we studied this object when written in this form. Okay, now we decided to interpret this as purely a correlation function that we can compute in free field theory. We learned many techniques to compute it. One of them was the weak contractions, or the weak theorem, which related the time ordering operator, or the expectation value of the time ordering of many operators, to something that looks like contractions, which give rise to Feynman diagrams. And we said that the numerator was given by the sum over all possible diagrams with two external points, and at order lambda to the m, because we're going to expand this exponential, so at order lambda to the m, the diagrams will be diagrams with m internal lines. So we said, well, we can start drawing diagrams. So this was the only diagram that we could have at order lambda to the 0. And then said, well, we can have a diagram like this. At order lambda, but we could also have a diagram like this at order lambda, and we kept going and adding more and more diagrams. Then we decided to rearrange a little bit this series, and we said, well, let's try to collect everybody that has, say, this diagram, and together with this guy, we will collect everybody that has this, and something that looks like this, plus something that looks like this, 2 copies of this diagram, and many, many, many copies of this diagram. Then we said that according to the Feynman rules, to compute the actual function of x and y that this thing depends on, this thing would agree with having this diagram and the contribution coming from this thing square, except that we have to put a half due to the symmetry factor. And when we keep going, we will have terms that look like 1 over m factorial, this diagram, and this diagram, the contribution of just a single one of these to the power n. Okay? Of course, there are many more diagrams. So this part of the whole answer can, of course, be resummed into something that looks like e to the this diagram. Okay? Now, what do we want to do? Well, let's look at the other diagrams, right? Now consider another diagram that looks like this. Okay? Let's look at this one. Now consider, well, let me use this symbol, this diagram. And now together with this diagram, let's combine this diagram. Okay? Now let's combine with this guy another diagram that looks like this. And let's keep going, combining every single diagram of this form with an arbitrary number of these guys there. Okay? So what do we get from this contribution? We get this diagram times exponential. So we get this diagram times exponential of this guy. Now take any other diagram, anything that you like. Say you can take this diagram if you want. Okay? Take this diagram. Now combine with this guy the same diagram, same as here, but now with 1 power of this guy. Now combine the same diagram with 2 powers of this guy, and so on. So what do you get? You get this diagram times the exponential of this guy. Okay? Yesterday, the argument I was using was not correct, and that was pointed out by Anthony, right? Anthony. Yes. Sorry. Yeah. So at the end of the lecture, Anthony pointed out that the argument I was using was not correct. So it was correct up to this point, of course, where we got this exponential. Then what we really had to do was to pick any other diagram that was not in this set because we already took it into account, then collect all diagrams of this form, exponentiate, take any other diagram, collect all these diagrams of this form, exponentiate. So after we keep doing that, what are we going to find? We're going to find that our correlation function, or our numerator, is equal to the sum over all diagrams without this diagram times the exponential of this thing. Do you agree? Do you agree? Yeah, you always say, that didn't sound like a very convinced yes. Well, so let's repeat the argument. We start, you pick any diagram you like. I like this one because it's the simplest one. So I start with this one, and I collect every single diagram that contains the diagram I picked together with one guy, with one of these guys, 2, 3, and any number of them. So by the symmetry factors, we pick this. They exponentiate. They give me this. Now I pick any other diagram, any other one, which is this guy, say, and I collect it with this set of diagrams. These pieces exponentiate. So I now got this plus this, but this factors out, right? So I have this plus this times the exponential of this diagram. Now I'm going to have this plus this times the exponential of this diagram. So I get the sum over all diagrams without this guy times the exponential of that vacuum diagram. Well, but these guys contain other vacuum diagrams, like this one, say, inside, right? Let's repeat the same argument for this group here, but now in order to remove these guys. This one. Now here, for these ones, I can take this xy plus xy, this guy, plus xy, 2 copies of this guy, plus any number. So what do I get? From this subset, I get xy times e times the exponential of that diagram. Okay? Now I do it for this one, say this one, together with this diagram, 1 time, 2 times, 3 times, any number of times, and then it exponentiates again. So once again, this guy becomes the sum over all diagrams that don't contain this guy times the exponential of this thing. Okay? So now the next time I get the sum over all diagrams without this guy and without this guy, and then the exponential times the exponential of this guy. Now I just keep going. Every time I see a vacuum diagram. Oh, from the symmetry factor, right? So, yeah, so if you look at this thing, the Feynman rules tell you to compute all the product of propagators, integrate, put the factors of lambdas, all that, and divide by the symmetry factor. This guy has a symmetry factor of 1/2 with respect to what this thing would be if we were taking just the contribution of these guys square. Okay? And this guy, we have it, well, the guy with n guys, we have an extra symmetry factor, which is 1/n factorial. Okay? Because we can permute these guys. So we keep going, and then you will end up at some point in, well, probably never, right? So you will never end because there is an infinite number of vacuum diagrams. But we can imagine that we finish this process. We will end up with a sum over all non-vacuum diagrams. Times the exponential. Now these guys combine. These are numbers, right? So these two exponentials combine. The next one combines with this, times the sum over all vacuum diagrams. And we ended the lecture by saying, well, the denominator looks exactly as the numerator, except that we don't have these insertions. So this must be the contribution from all the Feynman diagrams that are vacuum diagrams only. And of course, by the same argument, they will exponentiate. And we will get back this exponential. Is that clear? So our master formula yesterday was that the object of interest was simply given by the sum over all diagrams which are not vacuum diagrams. Okay, so that was the conclusion yesterday. Now, the same thing can be said for more complicated objects. Well, let's actually write down some of them, right? So now we can simply write this as a contribution from this diagram plus the contribution from this diagram plus higher orders, okay? So life is getting simpler and simpler. In fact, getting rid of these vacuum diagrams was very good because they were actually divergent, right? So it was very convenient that we could just cancel them out.
Is there any guarantee that these non-vacuum diagrams won't diverge?
No, I didn't say that, right?
Right, yeah. I mean, one problem.
One problem at a time. Very good. Yes, I didn't say that. So if you consider this one, it's the same, the sum over all possible diagrams that are not vacuum diagrams. And now when we study this, you will see why I don't like to call the diagrams that we get. In some books, and people call them connected diagrams, but I don't like that terminology because in this case, we're going to get diagrams of the form. We already got some of these last time. Okay. Clearly, these ones are to leading order, right? These diagrams are the diagrams that we get to order lambda to the 0. How about lambda to order lambda? What can we get? Well, we can get something like this. Plus other diagrams where I insert this interaction here in all possible ways to the diagrams that I already got. But is there something truly new that I can get? Well, yes, this guy. Okay. And this is the reason why we introduced this 4 factorial at the beginning of the whole story. Just so that for this diagram, we could simply write minus I lambda, right? Now, this guy has symmetry factor 1. So if you remember, that was the whole reason we introduced the 1/4 factorial. Because if we didn't have that, these contractions would give us 24 times the diagram, but then we are dividing by 4 factorial, so we cancel it. Okay? Very good.
Why is this diagram of particular interest? Like, why?
No reason, really. Well, you will see at the end, hopefully at the end of the lecture today, or at the beginning of tomorrow, why this diagram is of particular interest. Yes. Yeah, there is a particular, yes. Actually, there is something important about this diagram. But we're a little bit far to seeing why this guy is important. It will turn out that all these things will not contribute to a physical observable that we want to compute.
Is this somehow showing some sort of converging interaction?
Well, what do you think is the difference between this diagram and all the diagrams that I've drawn?
I mean, there is no, they're not interacting. All four.
Yeah, all 4 are not interacting, that's right. So this is the first diagram that is fully connected. Okay? So we're going to see that these fully connected guys are going to be very important for us. Okay. So, some problems. I know some of you haven't been able to sleep lately, especially you, right? Due to the problems. But what are some of the problems? Well, the first problem is that at the beginning, when we were doing this calculation in the numerator, we had all these factors of d for z's without anything. But these only appear in vacuum diagrams. So these guys are gone, so we don't have any problems. Now the next problem is that even in the non-vacuum diagrams, we have things like this, where we are evaluating a Feynman propagator at z minus z, which happens to be 0 indeed. Yes. How do we define this? Well, actually it's ill-defined, but let's just write a symbol for it. And the symbol we're going to write for this object at the moment is going to be in the form of the integral representation. So in the integral representation, this thing is d for k over k squared minus m0 squared plus I epsilon e to the minus I. Remember, we had this here. But since we're at 0, this thing is 0. So it's gone. And all we get is just this integral. This integral is ill-defined. Why is it ill-defined? What do you think? Sorry? It doesn't converge. Can everybody see why it doesn't converge? Where it doesn't converge? I mean, why it doesn't converge? What is a region of momenta that will give you trouble? For very large momentum, that's right. For very, very large momentum, this integral doesn't converge. if k is very, very near 0, this integral is completely fine, right? We have a mass term here. So this integral is actually very, very nice. Why did you think that it was going to give us trouble for a small momentum? Sorry?
Because of static. Yeah.
Oh, because you face a problem like this in statistical mechanics. Oh, well, of course, if you want to get trouble, you can always ask for trouble, right? Consider a theory of massless particles. Then you will get your divergence, right? So you want a divergence, you want an extra divergence, then just do it, right? Of course, in a statistical mechanics, the divergence for large momentum is actually not there, because at large momentum, we are exploring what is happening in our system at very short distances. And in statistical mechanics, at very short distances, all the continuous approximations break down, and we're thinking about a lattice, say. Yes?
So even if I set m equals to 0, the numerator integral will give me k cubed in a vertical length, which will cancel the k squared.
Yes, in this case, it doesn't seem to be, yeah, in this case, it's not divergent, even for m equals to 0, okay? But you could have suspected that there might be some problem, and there are other integrals that are divergent when you have m equals to 0. In fact, the first one is when you have 4 propagators, okay? So in Lorentzian signature, you can show that if you have 4 things like this in the denominator, it's the first time where you have an infrared divergence. It's called an infrared divergence because it has to do with very low momentum, okay? Now, back to the UV, the very high momentum, the very high energy divergences. Indeed, we know here that if we were doing a statistical mechanics, we will be exploring what happens at very short distances. And if there is some kind of lattice in our statistical mechanics system, we will reach the point where we cannot neglect the lattice size, okay? And then integrals will be replaced by a sum, and everything will be fine, okay? But here we're doing quantum field theory, and basically Lorentz invariant tells you that you cannot get away with having a lattice, okay? You cannot think about space-time as having lattice points, okay? So what do? Well, we just put a cutoff and say, well, something will have to happen at very short distances, which we don't understand, okay?
Discretizing space-time violates Lorentz?
Well, try to think about any way of saying that this point is special, and this point is special, and these points are special, and they are all that exist. Try to make a definition of that is Lorentz invariant. Well, first of all, it's not Poincaré invariant, right? Because it's not invariant on the translations already.
No, but lattices have translations.
Discrete translations. Okay. Very good. So we have this problem, we have that problem, and we also have our old problem of what to do with this thing. In fact, in principle, this is not a problem. I mean, this is a definition, I mean, we derive this, and this is the definition of the contour here. It's just that if we want to show that we have something that is Lorentz invariant, it will be desirable to get rid of this, right? Because then these integrals will truly be Lorentz invariant. The integrals that we now have for a space in the time direction have this funny shifted contour, okay? So we'll have to fix those two problems.
With respect to the cutoff, okay, I can put a cutoff here and everything is finite and everything is good, but so the results are independent of that cutoff?
If they are not, then we're doing something wrong, right?
So we'll put a cutoff and hope for the best.
Now you're learning. Now, yeah. After 6 lectures, yes. Excellent, very good. That's the spirit.
Did
Yes.
you say that the D4Z integrals went away with the vacuum diagrams? And so also
No, the D4 integrals with an integrand of 1. right? Remember, the vacuum diagrams have d4z's times only propagators that don't depend on the position, right? Because they are z minus z. So they gave rise to integrals over z, integrals over every internal point, over the whole space-time of something that didn't depend on that. So that was a very bad problem. But it went away, so no problem.
What did you say about the contour?
Well, we still have many more, right? Many more integrals over z. All these guys have integrals over z. Right? There is a z here. Okay? So in order to start learning how to deal with these problems, let's go to momentum space. So what do we want to do? We want to define a function that depends, that is nothing but the Fourier transform of our object, of our two-point function. This is the object we want to consider. Okay, well, let's do it. In fact, we know what this function is, modulo infinities and things that we don't understand what to do with them at this point. But at the very least, the first one is very easy to calculate, right? So this object has these two contributions. The first one is this. And this is just, the Feynman rules tell us to simply include a propagator or a delta f x minus y for this thing. But this in momentum space is given by d for k, I k squared minus m0 plus I epsilon e to the minus I k dot x minus y. Okay? Now it's very easy to compute the Fourier transform. We just apply these integrations to this, and what do we get? Well, for that diagram, for our first contribution, we're going to get something that looks like integral d for k, k squared minus m0 squared plus I epsilon. There is an I here. And then this guy with x and x here is giving us a delta function, right? It's giving us a delta function that logs p and minus k, or p and k together. Do you agree? That's the integral over x. So this came from x, from the x integration. Now we have to do the y integration. Well, we don't have to, but it would be silly not to do it. So the y integration gives p prime minus y. Okay? And that's our answer. Well, it looks pretty good because, first of all, we can carry out the k integration using one of the delta functions, and we get an overall delta function of p plus p prime. Yes, thank you. There is a sign. Sorry. This one. Oh, yes, sorry. Yes, there is a k. But it's a plus. So I got the sign right, the letter wrong, but the sign right. Okay, so we do the integral over k, we get this, and we get I over p squared minus m squared plus I epsilon. So this looks pretty good. In fact, it looks like in momentum space, the object is actually nicer. Okay, so there is this guy. Let's do the second one. The second diagram. So this was the first diagram. The second diagram that we want to consider is this guy. So let's call this 2 and this 1. So let's do number 2. So what is number 2? Again, we have to write down what it is. So we apply our Feynman rules. It says divide by the symmetry factor, put a minus I lambda times an integration over the internal point for every internal index, for every internal point. So now it's a z. Okay, so that's for the z that we have there. And just put all the propagators that you see. So we're going to put delta of x minus z, delta of z minus z, and delta of z minus y. These are the Feynman propagators. Okay, so this is a contribution of the diagram. I mean, this is the actual function that we represent by this diagram. But now we want to take the Fourier transform. So what do? We, once again, first of all, there is nothing to do with this guy. This guy is whatever it is. These guys we're going to write, again, in momentum space as d4, say, we can call it k1 I e to the minus I k1 x minus z over k1 squared minus m squared plus I epsilon. And this guy we can represent as integral d4 k2, say, I minus I k2 dot z minus y over k2 squared minus m squared 0 plus I epsilon. Okay? So when we compute the Fourier transform, what do we get? Well, let's get over with this guy first, okay? Let's put it in front. So that guy says an integral d4k or d4l, let me call it L. We need other variables, right? We're running out of variables now. I over L squared minus m0 squared plus I epsilon. And I decided that I'm not going to worry about this guy. Next, well, of course, we have our factors. And we have an integral d4k1 I k1 squared minus m0 squared integral d4k2 I k2 squared minus m0 squared plus I epsilon. And what else are we going to have? We now have to do the integrations over x and y and over z. That's where the z integration enters. Remember? Okay. Good. So let's do the easy ones. Let's do the integral over x. So what does the integral over x give us? Well, it's going to give us a delta function that logs p, it contains p, and everything else that contains an x here. Only here. It will be an integral over y. The integral over y is going to have a p prime, and anything that has a y here now is a plus k2. And now we have our funny integral over z, okay, of what? Of e to the everything that contains z. So we can say iz k1 minus k2. Okay? Now this integral is really this integral because we have our funny contour, right?
So what about the integral over L then?
This guy.
Oh, I see. Okay.
Yeah, I need colors. Yes. But now, if you look at this, you can see that this object can be thought of as somehow a regulated version of a Dirac delta function. So it's begging you to say, well, just simply take epsilon to 0. It becomes a distribution. That's why from the beginning it was a little bit funny, right? Because its job is really to regulate the distribution. But now that we're doing this perturbation series, it makes sense to treat this object as literally the limit when epsilon goes to 0, when this epsilon goes to 0, and treat this as a distribution. Yes?
But the only reason you managed to get so many things to cancel was by treating epsilon as finite. So we had an infinite imaginary part which cancelled, which sent everything to 0. If we then take epsilon to 0, how can we be guaranteed that we're still going to get the cancellation of all those terms?
You mean the derivation of this formula relied on epsilon being non-zero?
Yeah.
Yes, but all I'm saying is that once you compute everything, the quantity that we derive, now the epsilon dependence in perturbation theory, in this object that we're doing, in the way we're evaluating, only enters through this contour. And in this contour, we can simply set it to 0, okay? Somehow, its job was to regulate the distribution. Okay?
I think what Kieran said is, I thought the job was to kill off all the higher...
Well, that was a job in deriving the vacuum,
yeah.
in deriving the correspondence with the vacuum. Yes, indeed, it did something very important. But once we projected out that object, we get something whose only dependence on epsilon seems to be, or which only job seems to be regulating this distribution. So we just take it to be 0.
I guess the issue is that how do we know that the higher terms that we projected out don't contribute as well? Like the issue isn't with this term, the issue is that we need to consider other terms.
Well, to this order, the other terms will not contribute, right?
Okay.
In this calculation, it will not contribute. In fact, to any order in perturbation theory, they will not contribute because what is going to happen is every time we get an integral of this form in momentum space, its job is going to be regulate this distribution, okay, to regulate the distribution.
Can't you get away with that by saying just that without taking the limit, that is precisely a representation of a delta function, and when you take the limit with an epsilon is different from 0, it doesn't matter?
No, without, if you don't take epsilon to 0, this is not a delta function.
Yeah, but I'm taking the limit after I do the integral, right? So if I have the
well, that's the whole point, that I'm taking this as a regulated version of a delta function.
yeah, okay.
And then when we take epsilon to 0, we just simply get the distribution. Okay? Very good.
Another thing, that epsilon here is not the same epsilon that you have in your property.
No. Okay. So any other questions? Because from now on, we're going to assume that we don't have that. And this simply gives us another delta function. Okay? So who can come out with Feynman rules in momentum space now? Just by looking at that and by looking at this. I'm sure you can come out with, well, Feynman, yes, of course. Now, yeah, probably all the chalk is, yes. It's very strange. Tibra brought lots of chalk yesterday. Somebody stole them, yes, indeed. Well, okay, I think we can manage. Okay, so let's try to derive Feynman rules for computing the contribution of a given diagram in momentum space, okay? By looking at this and this. So from two examples, we're gonna try to derive the rules. Well, I'm giving you time while I erase this. to think about what the rules can be. Fourier transform what you had before. Integrate all the x's, and then, yeah, well, yeah. Very good, yes. So that would be the definition of the object. Now we want to find the rules. Okay. Well, let's look again at our diagram. For every external vertex, we put in some momentum, P, and some momentum P prime, right? That's what we did there. We introduced for every point in space-time the Fourier transform, so we're basically introducing momenta for every one of them. Now, the fact that each line corresponded to a Feynman propagator, it means that we can think of as having some momentum in this diagram, okay? So this corresponds to the momentum that appears in the Fourier transform representation of this Feynman diagram. So how can we get the formula that is over there? Well, I can simply postulate or say that the rules are that every time you see, first of all, a vertex, what do I have to do? That's right. For every vertex, I put a delta function that ensures momentum conservation. In this case, looks very trivial. It says that P minus K has to be 0. Sorry?
You implicitly use the arrows for the direction of the momentum so that the sign in the delta will be fixed?
Yeah, so I'm saying all the external guys, I'm taking them to be incoming.
Okay.
That's right. Well, after all, look, I chose the same sign for the Fourier transform, right? There is no distinction between x and y. These 2 points are the same, okay? So I have that for every vertex, I put a delta function. So that tells me that I need one delta function here and one delta function here. Okay? So for every vertex, so the rules are starting to shape us. For every vertex, put a delta function.
If x and y are equivalent, why do we have them switch in sign?
If
they're treated entirely equivalent,
yes.
then why do we switch signs?
Because K is an integration variable. So K is an integration variable. The formula is completely symmetric in P and P prime. I mean, the diagram is not symmetric. The diagram by itself, because I had to give an orientation for K.
Okay,
so that's what breaks the symmetry in the integrand, right? But the answer is completely invariant, right? Because now for each of these guys, every time you see a line, okay, now we're distinguishing the vertices from the lines. So for every vertex, you introduce a delta function. And for every line that you see, you introduce an integration over the momentum that is there times I. Okay? Of course, this diagram is too simple to give us the next rule, but the next rule should be that if this vertex is an interaction vertex, you should also multiply by minus I lambda, okay? So each vertex gives you this, and each vertex that corresponds or that is joined to 4 lines will give you a minus I lambda times the delta function that preserves momentum, okay? Now I claim that with these rules, I could have written down the second answer. Of course, there is one more, which is I will divide by the symmetry factor. Okay. So first of all, do you all see that we get this diagram from these rules? The answer that we have over there, right? We get the integration, which is there, the two delta functions, and that's the answer. That was very good. Now the next one would be, again, you have P, you have P prime, you have K1, K2, and L. That's our second diagram in momentum space. So once we have our diagram in momentum space, you look at it, you apply the rules. So we get 1, 2, 3 integrations over momenta over K1, K2, and L. We get 1, 2, 3 delta functions. We get a factor of minus I lambda, and we get a half from the symmetry factor, okay? But of course, this answer, just as here we got it to be something very simple, we could also get it to be very simple as well, right? It would be silly not to use these delta functions to carry out the K integrations. So this will give us our integral, a half minus I lambda. Now, these three delta functions are enough to localize these two, okay? So we can use this to carry out this integration, this to carry out this integration, and this last guy will give us what? Will give us a delta function that says, well, this guy is equal to P, and this guy is equal to minus P prime, so it will be P plus P prime. So we get delta 4, P plus P prime, okay? And these integrals will be done, and we get P square minus M0 square plus I epsilon. And actually, since P and P prime are one minus the other, the P prime that we will get from here becomes P, so we get all these square. Okay? So the Feynman rules that you will find in books are not these ones. That's why I call this one version 1.0. The Feynman rules you will find in books are the rules, that are a little bit smarter. The rules give you this answer already. So can we come out with rules that will give us directly this answer? Well, obviously, the first thing to do is not to do this silly thing that I did here, which is to say that we have a momentum P and here a momentum K1. We know that there is already a delta function here that will lock this P to be this K1, right? So we shouldn't even include this integration. This delta function will always carry out this integration, okay? So in the smarter way, so now Feynman rules. Second version would be, if you see a diagram, don't even bother to draw these points, okay? Just don't do it. Say that the momentum that goes here is P, the momentum here is P prime, okay? This momentum is L, and then what's the rule? The rule tells you to add, first of all, an overall momentum conserving delta function. What do I mean by that? Well, you see that this diagram had this delta function, and the diagram on top also had it. Could it be that all diagrams will always have that delta function? Well, the answer is yes. So all diagrams will have this delta function with the external ones. Can anyone tell me the reason? Why would that happen? That's a consequence.
Yeah, but you're always evaluating something that is by X, by Y, right? You don't turn only to external points.
I'm jumping ahead. So look, imagine we're doing something, we're evaluating this one in momentum space. So there will be 4 momenta. And then there will be, I claim there will be an integration, there will be a delta function saying that the sum of the 4 momenta that I use in the definition of the Fourier transform of that guy will have to add up to 0. How can I tell that that delta function will be there? Just by looking, exactly, translation invariance. We know that our formulas are translation invariant, right? Well, from the beginning, they are Poincare invariant, right? In particular, they must be translation invariant. But everything depends on differences of points, right? The propagators are only differences of points. So if we shift everything by a constant vector in space-time, we will get the same answer, okay? That shift is what implies is that this delta function has to be there always, okay? So this is a consequence of translation invariance. Okay, so we're very happy we put it there. What's the next rule? Well, every time you see an internal line, so if this is internal, okay, you replace it by a propagator. Okay. 3, you put delta functions for every internal vertex in fact, we could do this already from the start, right? From the start, we can look at a diagram, and instead of putting these delta functions, we say that the diagram actually tells us the flow of momentum, okay? So we could start by drawing the diagram and saying that the diagram has momenta flowing, and at every point, momentum has to be conserved, right? So we could even get rid of this rule, but let's keep it here, okay? And finally, well, almost finally, integrate over any internal momentum not fixed by 3. Okay? So once again, this rule, this part could be implemented at the level of the graph immediately. Okay? Let me give you another example. Imagine that we have a diagram that looks like this. Say, yeah, that's a problem with this theory. It has too many. Imagine we have a diagram like this. Okay? So what would the rule tell us? Well, we have momentum P1, P2, 3, 4, 5, and 6. Okay? So this momentum, we can already say that this momentum is fixed because we can remember that there is a momentum conserving delta function here that tells us that this momentum has to be equal to P1 plus P2 plus P3, okay? So we can implement this one already at the level of the diagram. And then simply integrate over anything that is left over, okay? In this case, we will integrate over L because this momentum conserving delta function doesn't tell us anything about L. Okay.
Sorry, by internal you mean like the remove?
This is internal. Internal means an edge that is connecting two vertices.
Okay.
Understanding that I remove all the external vertices.
Then why don't we have the I over the other two lines?
Oh, yes, that's right. Sorry. Yeah. There is a third version. Yes. Sorry. So for every line, yeah, sorry. I was actually jumping to the third version, which we will get at the end of the, yeah, sorry, it's not the final version. That's why if I keep if I keep putting things like this, it means that there will be a new version. So in this version, you're right, very good, very good. In this version, we have to replace every line we see with a propagator, even these lines. Yeah. Is that clear to everybody? I mean, otherwise, my rule will not reproduce this diagram. I missed these two things.
You need also to put the lambda term for its vertex, minus I lambda.
Yes, very good. So there is even a fifth rule, which is that we have to put this for every time we see an interaction vertex. We can put it where? Here, in the fourth one. Integrate over internal momentum. Not quite sure. Huh? I think it's safer to say that every time you have a quartic vertex in your diagram, right, a vertex of valency 4, you have to put a minus I lambda. Yes? Very good, yes. For every interaction vertex, I can put it here, so I don't need a new rule. So there is a fifth rule, yes. As you can see, I don't like to impose rules. Yes.
One thing, I don't know if it's just for this diagram, but this third rule somehow is
the third rule.
Redundant with the other ones, right? Because, I mean, can I just say that for every line that will show, I mean, for every line I put a propagator and just integrate over internal lines?
No, that was this rule.
Yeah, but you're integrating even, I mean, you're integrating here over L.
No, I'm integrating over any momentum that is not fixed by the previous one, yes.
So, I mean, I think I lambda has to be a different rule. We cannot put it with number 3 because that diagram that you drew with 6 external lines, there is no internal momentum which is not fixed.
No, for every internal vertex.
Yes. Oh, I see. So
I mean, internal, really, we remove all the external vertices. So there is not even an internal vertex, right? There is a delta function for every, here I remove, you see the problem with putting the minus I lambda here is that I said that graphically we can get rid of this by simply drawing the graph, right? So that would be a little problem with putting the minus I here if I want to remove this from here, right? So I think I'm going to settle down after all this discussion for saying that we draw the diagram, we impose momentum conservation as much as we can, okay, from what we see in the diagram, from the flow, okay, and we replace this rule by saying that we just put this factor every time we have an interaction vertex, and we integrate over all the momenta that are not fixed after we do our little game of following momentum conservation through the diagram, okay? And exactly these 5 rules are the ones you're going to find in the books, okay? So we ended up converging to these rules, okay? But as I said, there is still another set of rules, but it's for computing something slightly different. Now let's keep going and study a little bit more our momentum space object, okay? Any questions so far? Okay. Sorry?
The last thing to the quiz of the delta function.
We're going to impose the delta function in the vertices by drawing the diagram, okay? So let's actually do one more. Say, let's do it here. Say we have this diagram. This could have been one of the diagrams that contribute to the 4-point correlation function in momentum space, right? So what would this diagram give us? Well, we have the two internal guys, so we put a minus I lambda square, okay? Then we have to, the first thing we do is to apply momentum conservation without doing anything to our expression, but only looking at the diagram. So we have that there is momentum conservation here, P1 plus P2 going here, right? But we don't know how to split it. So there must be another momentum that we cannot fix by momentum conservation. So we can just call this one L. So what would be this momentum here? It would be, if we define it to go in that direction, it would be L plus P1 plus P2, right? This one would be P4 and this one would be P3. Of course, none of this will make sense unless we remember that there is a delta function that tells us that P1 plus P2 plus P3 plus P4 is equal to 0. And then we can apply the rules and construct the rest without having the rule that I had before for the internal vertices. Is that okay? L is not fixed, so you have to integrate over it. Okay? Yes. Okay. Very good. So let's move on. And let's do a little calculation. Well, it's not a calculation, really. It's just an observation about our object GP P prime. As we know, this object contains this delta function. So let me define the rest to be something that depends only on P. Okay, so yeah, I don't know how to call what we're going to do now. Let's call it. Let's call this section resumming.
Does it matter which direction you pick for your momentum to go into? So would I have to worry about putting minus L or plus L?
No, it doesn't matter.
The relative sign,
no, the direction doesn't matter. I can define this momentum. If I had defined it going in the other direction, then this would have been minus L minus P1 minus P2.
Freddy, I think it's L minus P1. Minus P1 minus P2.
Indeed, yes. No, sorry. This guy, These guys are incoming, this guy is outgoing. So in fact, it should have been, yes. No, even if I change the arrows, it's not correct. Very good, yes. Okay. So what is the momentum? Going inside is P1 plus P2. So if I want to say that this momentum is going outside, say, it would be P1 plus P2 must be going out. But this guy was going out. So maybe I should have defined this guy going in. It would have been better. And then the previous answer was, oh, you were right. I only had to reverse the two arrows. And then you have been correct. Very good.
With respect to the symmetry factor, when I put labels on my external line.
Yes.
So the symmetry factor, how do you calculate it in this case?
Exactly in the same way as we did before.
Even, I mean, so for every internal line, there will be more equivalent diagrams.
Now, the symmetry factor is the same as the symmetry factor we had before. You calculated it in exactly the same way.
So that's half, right?
In this case, it could actually be, so you can swap these two guys. Yes. I think it's probably half. So let's expand this guy, okay? We have this term, Now the next term would be what? Well, we can have something that looks like this. Again, by momentum conservation, this P has to be the same as this P and this P. Okay. We could also have this guy. We can also have this guy. We had it before. What else can we have? Well, we have tons of things. So to order lambda square, is that all that we can have? Anything else that I'm missing? To order lambda square. It's probably what we have. So lambda 0, lambda 1, lambda square. Now we can keep going if we want. We can do something like this. And so on. Okay. Now let's do the following. Let's classify diagrams according to the following rule. If you see a diagram here that can be split into two completely disconnected diagrams by only chopping off a single line, then it's funny because I want to give a name to the other guys, not to those, but okay. So let's see which guys are those, okay? Let's distinguish those. So this, I can disconnect into two different diagrams by only chopping off one line. There is no line I can chop here to get two different diagrams. No line here that I can do, a single line that I can do. Here there are two lines even. So I can chop it here if I want, this one here, this one here, okay? So people like to call the diagrams that cannot be split into two. So diagrams that cannot be separated by chopping a single line are called one particle irreducible, or 1 pi. Very appropriate, huh?
What about the first one?
The what? This one?
Yeah.
I cannot split into two diagrams, right? What do you mean, two lines?
So the chopping is only for internal. You're only allowed to chop an internal.
Yes, indeed. Yes. Very good. Yeah, I guess logically you're correct, right? That if I'm able, if I can chop this line, who tells me that this line is not is different from this one? It looks the same, so why not chop it? well, let's see what it includes, okay? Well, let's actually define more carefully what I mean by chopping on what we get, okay? So this guy, right, give us I over p squared minus m0 plus I epsilon, right? Plus this guy, okay. So what I want to do is to take this guy, and then we're going to see that this guy gives us 2 powers of this thing. Times something, okay? Times this thing here. So let me call it, what notation do I use? So actually, let me call it gamma 1, for the lack of a better name. That's whatever comes from this guy, okay? Very good. So let me call this diagram 1, this is diagram 0, okay? The next diagram that cannot be separated into 2 is this guy, okay? So I'm going to get the same 2 propagators, right, times a contribution from the next guy that I cannot separate into 2. So I look again, I say, well, this guy can be separated into 2, this one 2, this one 2. So I have to keep going and find the next one that cannot be separated into 2, okay? So try to find out what the next one is. And if you do, write it in a piece of paper, you can show it, and then I can draw it on the blackboard. So the next one, and there is an infinite number of them, okay? In fact, the next one, well, one of the next guys is actually very simple. In fact, it's this one. Yeah, we missed that one. So that's gamma 3. So we can have gamma 4 and all of them, okay? So I'm going to give a name to this sum. So people like to call this a circle with a 1pi label in it, okay? So we have this 1pi, and if we have these 2 propagators, people like to say that you have this guy with 2 propagators attached to it, okay? So this would be the 2 propagators. Now this guy is our single propagator. Now we can look at these other ones, okay, and say, well, what do they look like? Well, one of them could look like this thing times contributions that exactly look like these contributions that were coming from the 1pi pieces that I had here, okay? So in a sense, I can rearrange the other diagrams so that I get, say, this diagram times every single thing that I had in the 1pi expansion, okay? So once again, I can rearrange the diagrams and get something that looks like this. But once I have all these guys, I can also put on this side everything that looks like 1pi again, and then get a new contribution that looks like 2 pieces of 1pi connected by 3 propagators this time. So the whole expansion can be replaced by an expansion that looks very amusing. It's just the free propagator plus this whole thing plus Remember, by this I mean an infinite number of diagrams plus this guy plus the contribution where we have 3 1-pi guys, 4 1-pi guys, and an infinite number of PIs, of 1-PIs. Now, this contribution, people like to call it minus I sigma of P, which is a function of momenta, okay? So this is just a definition of this function, assuming it exists, right? So if you assume that such a thing exists, we're going to call it sigma of P. Okay, so if that's the case, what is our function g hat of P? Is equal to I over P squared minus M0 squared minus I epsilon plus, what do we get here? We get 1 propagator times this propagator times this 1-pi contribution plus this guy has 3 propagators. One of them, I'll pull it out as I did before. And then we have this 1-pi with this propagator, 1-pi with this propagator, give us exactly the same factor that I have here, but it's squared now. The next diagram will give us 1 propagator we can pull out, and then we will get 3 factors of the same thing, and then 4 factors. In the end, we will get a series. Nope. No, there is no symmetry factors here. Well, the symmetry factors are in the individual diagrams. But once I collect them like this is all we have. Okay? So we're going to have I P squared minus M0 squared. Oops, this is a plus I epsilon. Why did I put minus everywhere? Okay. And then we have the sum over n equals to 0 to infinity. N equals 0 because we get a 1 from this term of I. You must be thinking that I'm stupid because I'm not canceling these 2 factors, I and I. But let's just keep them. Actually, I'm stupid. Why not cancel this? Why not cancel the factor, right? I mean, I thought there was a deep reason. I'm sure there was, and then I'll regret it. To the end, okay? Now we look at this and say, oh, isn't this nice? Yeah, it is, of course. I mean, every time you see...
Yes. That's only
Isn't that this?
only if x is more than 1.
But nobody told you what M0 was, right? So M0 could be very, very large. So this thing could actually be very, very small. Oh, please, a little faith here. Remember, this is M0, right? I haven't told you what M0 is. So we get 1 over 1 minus this whole thing, which is sigma of P over P squared minus M squared 0 plus I epsilon. That looks pretty good. So just to compute this object, all we have to do is to compute this sigma, and we're done. Oh, thanks. And now we can go. Now we can finish the lecture. we are only 5 chalks away from finishing the lecture. So
How do we know if those are the modulus of those terms is less than 1?
because M0, I haven't told you what it is. Gonna make it big. Sorry? That sigma is what? It's not infinite. Well, sigma is not infinite because remember, we're regulating our integrals with a cutoff. Oh, you're saying, could it be that the sum doesn't converge? Well, you're so picky. And
So nothing converges, but we make it converge.
so we put this guy inside here. This cancels this, and then we get something that looks like minus sigma p plus I epsilon. So isn't this nice? So that's the full answer. It looks like, so this 2-point function actually looks like a Feynman propagator, except that in the Feynman propagator, we would put here a mass square. This is what we would do in the Feynman propagator, right? But there are little problems, like this thing depends on momentum, okay? So it's very tempting. But we're not there yet. So let's keep this for a little bit. And let's actually see. We're going to switch gears in order to be able to use this result. And we're going to go back to the fully interacting theory, back to thinking this is going to be exciting, huh? Back to thinking about age. Ooh. And phi. How about that?
I never get why things are funny.
They are not, but then it's. I mean, it's a sign. It's a sign of desperation, on my part, right? So, well, we have to go. It's.
I think it's an important part of the course, getting the joke.
Okay. Well, every time we're thinking about H and phi and the fully interacting guys, it's because we're going to make assumptions, right? We don't know how to prove them fully. And we're going to make an assumption about the spectrum of H. Okay? So we're going to assume that our fully interacting theory has excitations that look like particles, okay? And not only that, we're going to assume that the Hamiltonian has a spectrum that is called nice, okay? So what's the spectrum? Well, just like there is a Hamiltonian, the Hamiltonian is the zeroth component of the momentum operator, so there would also be a 3 momentum, P, say. So we can draw, I wonder if we want to draw it here. Yeah, why not? So we have P, and we have the Hamiltonian, okay? Here, by this, I mean the eigenvalue of the states, okay? And the same thing here. So we're going to draw the null con, okay? And then say, the first assumption is that there exists one excitation that we can call a particle, or there exists a state that we can call a single particle state, which we're going to call, I mean, people, Peskin and Schroeder call it lambda, 0. So this is a one particle state of mass m and momentum 0. Okay? 0 for momentum, 0, 3 momentum and a mass m. So this is otherwise known as a particle at rest. So we're assuming that our interacting field theory has a state that describes a particle sitting somewhere and has mass m. I think it's a reasonable assumption. Okay? So where would that particle be in this plot? It would be here. Okay? So there is a particle of mass m, not moving, and it's just here. Sorry? Oh, this is a state, right? We don't say that there are states with definite momentum.
You said the thing is not moving.
Yes, but I didn't tell you.
So I misunderstood.
It's a particle. It's a particle. One thing is that the state exists, and the other one is that you can actually measure it, right? The uncertainty principle is something about measuring. Okay? So this is a state that describes a particle of mass m, okay? And it has 0 momentum, but if you wish, we don't know where it is in the universe, okay? It has no definite position. It only has a definite momentum, which happens to be 0 momentum, 0, 3 momentum, okay? Yeah, so I misspoke. The particle is sitting somewhere in the universe. So I said here, but I didn't really know it was there. Yes. No, yeah, it was completely correct what you said. Okay, very good. So now, if we give a kick to that thing or we move, then to describe that the same particle, we need another state. We need the states with actual momentum p. Okay, but those states will have 3 momentum p such that p squared is equal to m squared. So they will all sit in a hyperboloid here, okay? So this is a space of single particles, of single one particle states, okay, of mass m. We will assume that there are no other states that look like that, okay? Our theory only has one such guy, and it's all hyperboloid. Then, of course, at some point, we will reach the 2 particle states, and then there will be a continuum of states with energies that can start at 2m, okay? So there will be multi-particle states. Okay? Yes?
You're saying that states with different mass correspond to different particles?
Yes, states of different mass, yes. So here we're assuming that in our theory there is only one.
So this theory won't give anything about antiparticles or anything like that?
It's a real, so yeah, that means it's a real scalar field. And I'm hoping that all of you have done or are doing your homework, right? In which you are studying a complex scalar field, and the complex scalar field has 2 excitations, a particle and an antiparticle. Both of them have the same mass, okay? But in that theory, we have 2 different particles. Yes?
So you said after the 2 particle state, it becomes a continuum?
Yeah, it becomes a continuum, right? Because the energy of the system, when you have 2 particles, can now take any values greater than this. Right? It's a system of 2 particles. Of course, in different theories, you could also have bound states, which we have energies lower than this. But for our case, let's assume we don't have any bound states. Okay, bound states would be between the 1 particle states and the multi-particle states. Okay.
So E is the total momentum?
Yes, the total 3 momentum. Yes. Okay. So if we have that, then what time is it? Oh. I just want to get to the point where we can use our spectacular result over there, okay? So all we have to do to get to something where we can use that formula is to say that is to write the same formula that we wrote in quantum field theory 0, which was basically that in the one particle states, or actually in general, if we know the spectrum, we can write the identity, or we can write the completeness relation in the Hilbert space of our Hamiltonian as follows. So this is our vacuum. Now we can write the one particle states. And the one particle states, if you remember in QFT0, we wrote them as follows. There we said, well, there was a parameter m, right, in QFT0. We didn't say what it was. We assumed in QFT0 that it was the mass of the particle, but here we see that it's actually the mass of the particle what we have to put in there, okay? This is the integration over the hyperboloid of one particle states. So we can call this lambda the one particle state with momentum k, and the one particle k with momentum k. And these ones are relativistically normalized. So they are slightly different from the free particle states normalizations that we had. Do you remember? The usual states that we create with A dagger don't have a relativistic normalization. We derived last week what the relativistic normalization has to be. These ones are assumed to be Lorentz invariant. Okay, not Lorentz, the same I miss speaking again. So these guys, these things together, these two guys together is assumed to be Lorentz invariant once we integrate over k, okay? This thing is Lorentz invariant by itself. Nobody is asking about the plus. Do you remember what the plus was? Yeah, the plus meant the delta function. So this was k squared minus m squared theta of k zero, okay? After all, we are only integrating over the hyperboloid, the upper part, okay? Now, what do we want to do with this? We want to go back to our object. So let's assume, let's take, this is again, these are the real objects. So let's write this as x0 minus y0. Okay, plus one more term. Let's concentrate on the first term and add to it the identity, insert the identity here, and let's see what we get. So we get
what happened to the time order?
It's here. I'm taking the first term.
Oh.
Sorry. Okay, so let's take the first term. Just 2 more minutes, and we will get the conclusion we want to actually make use of our formula over there. So there is another term. The next term is an integral d for k delta plus of k squared minus m squared. Now we have this guy with the field phi of x lambda k the field y and up. Okay? Very good. Now, what we have to do is to use translation invariance we use the translation operator to write this as e to the I px. So we're going to translate our field. Remember, this time we're allowed to say it, right? Because we're using the full Hamiltonian and the full momentum operator. We can now take our interacting field and translate it anywhere we want. So guess what? I'm translating it to the origin in time and in space.
Are you ignoring the higher, like your two particle states?
Yes, that's right. So there are more states. So we do that to phi of x, and we do that to phi of y. And then what do we get? We get an integral d for k. Now the vacuum is assumed to be Poincare invariant. So this guy acting on the vacuum gives you the identity. Nothing happens. So we get phi of 0. Now this guy acting on your one particle state, remember this guy is assumed to be an eigenstate of the full Hamiltonian and of the full four momentum operator. So this guy is going to give us e to the I k dot x. When we do it on this side, we get e to the minus I k dot x and k dot y, right? Because now on this side, we have to put the minus sign, or sorry, this time we get a plus sign, okay? When the operator acts on the one particle state. So this is looking very good. Now this state we can actually connect it to the state at the origin by acting with it with a translation, with a Lorentz transformation, with a boost, okay? So we connect it by applying a boost. Okay, here we are assuming that these are scalar particles. So there is nothing else that we pick up. There is a unitary operator that connects this guy with this, okay? Now the vacuum, of course, is invariant under a boost. So the vacuum, we can write it as U dagger. And when we put all this together, we get the action of a boost on phi at 0, okay? But this field at 0 is actually invariant under boost. So what do we get? So this is taking more than 5 minutes.
Why the field's invariant under boosts?
Let's get to that. So let's just, once we do that, this implies is that we get this guy is actually, can be replaced by this guy at 0. And we don't have any momentum dependence. These two factors factor out of the integral. And then we learn that our object, so what is it that we're computing? We're computing this guy. Yeah, this is taking too long. Has a contribution that comes from the first term, right? We're just looking at the first term. And that contribution contains something that looks like this, the absolute value of this, at 0, square, times an integral over d for k, delta plus of k squared minus m squared, e to the I k x minus y, okay? plus the other terms that we haven't done. Now, it's your exercise to show that the other terms will actually give us something very similar to this, okay? So the other term, so compute the other term, the contribution from the term y0 minus x0. And then you will find that we get something that looks like this. So let's actually give a name to this object so that I don't have to write it again. People like to call this z. So we get z times this theta function minus y0 times this integral plus something else you will compute, and you will show that it's actually proportional to the same object, plus something else that looks almost like this one, multiplied by another step function. And this then, you should be able to show that it's nothing but, what do you think? Yeah, by now we're not thinking, right? It's a Feynman propagator. So we have something, this thing actually becomes the expectation value of something that looks like a free theory, right? But now with a mass m, this is the full mass of our particle, right? We don't know what it is. Our theory has some particle of mass m. We can measure it if this was a physical theory. So this will be a physical parameter that we can measure. And this thing would actually become the Feynman propagator. So this object will have a contribution that looks like z times a Feynman propagator. So we will have something that looks d for k over k squared minus m squared plus I epsilon. This I epsilon is implementing the the step functions times I e to the I k dot x minus y. And there will be other terms that I'm not writing, okay? The reason we're doing this is that we want to use our formula for something. We worked so hard to get that formula. There will be a pity not to use it. So we got this formula. Now we learn from all this actual discussion that this object, this is g of x minus y, or the full two-point function, has a structure that looks like this. So if we Fourier transform this guy, what are we going to get? So what we learned from there is that if we Fourier transform the full physical object, we're going to get something that looks like z p squared minus m squared plus I epsilon plus other stuff. This will be the Fourier transform of this object. This is something that doesn't depend on momentum, so it doesn't enter in any of the discussions. It doesn't depend on x and y, so it's just an overall object. So we learn that GP has this structure, okay? But from our previous computation, we learned that GP was given by something that looks very similar, okay? So how do we put the two things together? Just by saying that the two things are together, we end the lecture, okay? These two things must be the same. How can we use the fact that these two things are the same? Well, it doesn't look quite obvious, okay? So let me suggest compare them at a momentum p0 that happens to be equal to square root of p squared plus m squared. So what happens to this object at that point? Remember, this is what we call omega p, or omega k. So if we evaluate this object very, very close to this point, what happens to it? It diverges. And what happens to this object? We don't know. It must, because the two must be the same, right? So it must be that this guy also blows up, okay? So how do we ensure that this guy blows up?
Sorry, why does it diverge?
This.
Yeah.
Oh, because this p squared is p0 squared minus p squared. And I'm evaluating at the solution where this is equal to 0. So I'm setting the denominator to zeros, making this blow up, okay? This guy doesn't look like it's blowing up. So we have to force it to blow up, okay? So how do we force this guy to blow up? So force p squared minus m0 squared minus sum over p plus I epsilon to have 0 at p0 equals to wp. But when this happens, p squared is equal to m squared, right? Well, let's actually do it. So at this point, p squared becomes m squared minus m0 squared. This just became m squared. And this is something evaluated at our special value. So we can call it star if you want. The epsilon is irrelevant. For the presence as a rational function, the two must be the same. So we can forget about the epsilon. So we need this to be 0. And guess what? This is then an equation that defines our parameter, which we didn't know what it was. Okay? Sure enough, this thing can actually blow up, right? When we take our cutoff, lambda, this object can actually be as large as you want. And then this guy will also have to be as large as we want. Yes?
Should I be worried that the expression on the left-hand side is imaginary and one on the right-hand side is real?
Sorry, which expression is real? This one.
This one, well, that one has an I on the top, the other one doesn't.
Yeah, the other one does. It's just that I didn't put it. Yes, thank you. That's why you were not surprised by the whole thing, because you were worried about the I. Yes, there was an I, yes.
So doing for the expression on the right, we know that the succeeding terms are decreasing in size?
Yeah, they are actually analytic at P0 when P0 takes this value, okay? There is no other contribution, yes?
So are we worried about the fact that
Well, that's actually a very good question. You see that all I did was to impose the condition that the pole, the location of the pole was the same. Now I should also impose that the residue is the same. And that will determine this thing in terms of sigma and M0 again, right? So this was only the location of the pole. So I made sure that they blow up at the same point, but I haven't made sure that they blow up with the same constant, with the same, with the same residue. So I should also make sure that that happens, okay? So this is our first example of a regularization procedure. And in fact, it's going to be our only example. In the next course, you will study the normalization of the theory. And in any theory, if you're lucky, okay, well, not if you're lucky, but in any theory that you want to study, you will have parameters that enter in the definition of the theory, like M0 and lambda that we had, or the lambda that enters in the interaction. And those parameters, which we don't know from the beginning what they are called bare parameters, okay? So this M0, and actually, I should have used, when we define this, we should also call this lambda 0. So M0 and lambda 0 are called bare parameters. Okay? And people were very surprised that you could actually make sense of the perturbation theory when you get infinities all over the place, like the ones we were finding, by simply absorbing those infinities in ways similar to this, by defining physical objects like the pole of the full propagator to be at at the mass of the particle square. So this is a physical requirement. Doing that fixed completely what this thing was. And now, well, this guy also enters here. Now something else has to be done so that this one will be correlated with the physical four-particle interaction. So you have to measure, if this was a physical theory, the strength of the interaction. You will get a number. You will measure the mass of the particle. And with those two numbers, you are supposed to be able to make sense out of the whole perturbation theory by absorbing all the infinities in the bare parameters. Okay? Now, would that happen? It turns out that it happens for this theory. But if you have an interaction with phi to the 5th power in 4 dimensions, such a thing will not happen. Okay? You have one more parameter if you want, so the coupling of phi to the 5th. But then it will be impossible to absorb all the infinities in that coupling. Okay? So theories where you can do the little miracle that I explained here are called renormalizable. Okay? And theories where you cannot do it are called non-renormalizable. Okay? So the theory we are considering, lambda phi to the 4th, is an example of a renormalizable theory. Can you tell me a renormalizable theory in 6 dimensions? Lambda phi cube. Okay?
Why lambda phi cube?
Well, I guess you found it by analogy, because in this case, this was a theory that was with a coupling that was marginal. In 6 dimensions, the coupling that is marginal is a coupling of phi cube. Okay? Phi cube in 4 dimensions is also renormalizable. In fact, it's even more than renormalizable. It's called super renormalizable. But you will discuss that in your quantum field theory 2 course. Okay?
So
yes.
If it
I
happens,
think.
I mean,
Not so much by cube.
Well, but yes.
so in the lab, you measure a finite value for the mass of a particle, right? So in the case that sigma of P star diverges, M0 has to diverge somehow to cancel the
Yes,
infinity.
indeed.
So if I go back to the Lagrangian and to my action and all of that stuff, from where we derive this, then I have M0 pops up, right? It's something that is divergent. So how can I justify everything that I did if M0 is divergent?
Well, that's a good question. Well, the physical, you simply assume that M0 will depend on your cutoff, right? And then the point is that any physical observable that you compute, following the rules that we have just laid down, must be something that can be expressed fully in terms of the mass and the renormalized coupling as well. Okay? So it should be something, the physical observables should be something that remain finite as you take the cutoff to infinity. Okay?
So something that is not clear to me, when you said that
Yes.
field theory is renormalizable if I can do this, right? What do you mean by that?
Well, it's not this. This is a way to define what M0 is in terms of the physical object, right? What I'm saying is that when you do the perturbation theory for a physical observable, okay, for correlation functions that have more fields, you will find infinities, okay? The point is that once you perform this condition, once you fix this condition, and you do something analogous for the coupling, then all those things would actually become renormalized at the same time. You don't have to do anything extra, okay? It's very surprising that then the whole theory becomes well-defined once you do this and you do the same thing for the coupling.
Okay, so a priori.
So maybe we should end here because we are over time. Then you can ask questions after the lecture.